So for today's class, we're going to go into the chapter of electromagnetism. We are going to see what electromagnetism is about and how we can also produce electricity, which is electromagnetic induction, EM induction, sometimes we call it for short. And one thing that I would like all of you to acknowledge that in this chapter of magnetism, electromagnetism, we don't have much math. There is only a very small formula pretty much at the end of the chapter, which is the formula for the transformer. How does the voltage and current of a transformer, primary coil, secondary coil, is related to the number of turns of the primary and the secondary coil, which is a very simple formula. And there is nothing else in your syllabus for the mathematical part for this whole topic altogether. So all the questions that you are gonna have, all the questions that we're gonna discuss are very blatantly, very deeply lying underneath the idea of understanding. So you gotta understand things right so that you can answer the things properly as well. This is really very important. And this might sound a little bit scary. I mean, if I was a student, if I came across to learn about a whole big topic that has no maths in it in my first chapter, I would be, I'd feel a bit moved. I mean, in the scary division. But one thing that I would like to assure you about of this fact is that electromagnetism, the topic of electromagnetism, the basic underlying principles that you have to remember, I can say that you have to memorize, which, I mean, the part that you have to have a grasp on in your brain, that is actually pretty small. There are very few tiny bit of ideas which are going to be delivered to you that here is a scenario. Whenever these things all come into one place or all work together, this is the outcome. This is the kind of situation that you're going to have. But that simple piece of theory can have so many different variation of application. So as long as you understand the underlying principle properly, you would be able to explain those scenarios pretty easily as well. So it's really important that you understand how it actually works at its core. Once again, like I have told you in the beginning of the magnetism chapter, that I'll be discussing a lot of what's, not a lot of whys. So I'm going to tell you what happens and what what factor changes what. But for most of the parts, I'm not going to be explaining the absolute physics relevant reason for why that work that way it works. And just to help you remember a small bit of thing that, let's not get there. I'm going to jump right into the whole topic. The first thing is that okay. The first thing that I'd like to discuss is that moving charge produces magnetism. This is a statement. Try to remember it. We're not going to get into the idea why does a moving charge produces magnetism. Just accept this fact that moving charge produces magnetism. Let me elaborate what it actually means in terms of ideas. Whenever a charge moves, it produces a variation within its electric field. The rate of change of electric flux, I mean, the amount of change that happens to an electric field. I mean, let me try to elaborate what I mean by this. Let's say we have a point charge over here, and it has these electric field lines coming out of it, which are radially outwards. It should be uniform, but this is a positively charged particle over here. So uniformly distributed electric field lines. Now, for an isolated scenario, let's assume that these field lines are infinitely long. Now, if I start to move this charge particle, positive charge particle, to the right, that is going to cause these field line orientations to change as well. And those variation of those electric field lines is going to bring about a change in the electric field orientation or the equipotential lines around this whole charge object. This variation of the orientation of electric field is a measurable quantity. How fast does this change happen, or that give rise to magnetism? You don't actually have to understand this concept properly. I am trying to give you some small bit of idea that how this is actually represented in the visual effect. But for your level, understanding or being able to remember this line is good enough, that whenever charge particles move, they produce a magnetic field, magnetic effect around them. What kind of magnetic effect? Where do we get the North Pole? Where do we get the South Pole? I'm going to get into that. But what I need to understand that if you have a charge particle, that to understand, if you have a stationary charge particle, it will only produce an electric field around it, a stationary charge particle. However, if you have a moving charge particle, it will definitely have its electric field. That will definitely be there because it is exhibit property of the charge. But because of the movement of the charge, an additional magnetic behavior would come along. And that magnetic expression or magnetic behavior or that magnetic property exhibit will only exist as long as that charge particle keeps on moving. The moment the charge particle stops moving, the magnetic property would be gone. So I'm going to put it in simpler terms that charge particle, whether moving or not, or I mean whether stationary or moving, will always have electric field around them. Stationary charge particles don't have any magnetic field around them. Moving charge particles do have magnetic field around them. So that's the basic idea. The charge particles can produce magnetism. So if you think that how does the charge particle actually produce radiation? And that's a pretty interesting idea, is that where we have to understand the key concept of a three-dimensional direction system. Three-dimensional direction system goes like this. If you consider a three-dimensional axis system, which is very difficult to draw in a two-dimensional plane, but I can try to draw it to some extent because we are sort of acquainted to this kind of figures. Let's say if this is a base of a certain cuboid, and if I try to draw another rectangle over here, parallelogram over here, another one over here, might as well rub this other part. So if I show you a figure that looks somewhat like this, this for our regular understanding gives us a sensation that this is a three-dimensional cube object because it appears to be a cube. But you can see it very, very clearly that for the way this figure is working, these angles, if we measure by a protractor, they are not essentially 90 degree. The reason they are not 90 degree because we are trying to represent a three-dimensional object within a two-dimensional plane. So that's why all the three dimensions could not be shown at perfectly 90 degree angles because this is simply impossible. Three-dimensional objects cannot be properly represented on a two-dimensional plane. The reason this figure makes sense to us because we have seen this kind of shapes like boxes, like wireframes, like bird cages, like glass panel boxes, crystal letters, or glass cubes, or those kind of things. We have seen these kind of things, and this shape is known to us by our regular visualization experience from day-to-day life. That's why a representation of this shape gives us the sensation of a three-dimensional object, although this is definitely not a three-dimensional object. This is a two-dimensional drawing of a three-dimensional object. So to make sense with the appropriate idea of three-dimensional object, we have to somehow bring about the idea of depth within this piece of paper, which is basically a two-dimensional paper. For example, over here I can draw an x-axis. Along this side we can draw an y-axis. And if I want to consider the z-axis, that has to either coming out of the paper towards you, let's say from this point, that z-axis should be in your direction and negative z-axis might go in the opposite direction. So what I'm trying to mean is, if you just try to look at any corner of your room from your position, just try to have a look at any corner of your room. Maybe a corner is not visible for some furniture, doesn't matter. If you try to visualize any corner of your room, try to have a look that the line that is going from the corner to the right on the floor, consider that as the horizontal x-axis, and the z-axis can be the vertical one, vertical side. So I could actually also represent this side as z-axis. Actually, in most cases, this is represented as the z-axis, and the perpendicular axis, which I can also once again draw slightly wrongly to represent a three-dimensional axis system. This can be given as the y-axis. And now, if you might wonder that why do I have to bother to write them x, y, z? Couldn't I write x, the vertical one y, and then this one z? We could, no big deal. We could name any of these axes as per we want, x, y, z. That sequence really is not much of a matter for your level. But what I want you to visualize that for a three-dimensional space, if we want to define a certain object in three-dimensional location, we need all the measurements. We need the x-axis coordinate, or we need the measurement of the along the x-axis value. We need the y-axis coordinate, and we also need the z-axis coordinate. So how do we represent that in a three-dimensional scenario? We represent the third axis, which should be perpendicular to our two-dimensional piece of paper. That might be your question paper, that might be your exercise book, that might be your actual study book, or that might be the screen that you of the device that you're looking at. This is a two-dimensional surface. That third dimension should be vertical or perpendicular onto this surface, which means if I try to draw a line, let's say this is an axis system of x-axis and y-axis, axis and y-axis. If I want to draw a z-axis right over here, I am trying to visualize a line that is going to penetrate through this dot into my screen behind my monitor, and that should also come out to my eye out of the monitor as well. That kind of a straight line, if you can visualize that, that is going to be our z-axis. Does it make sense? Somewhat.
Yes, sir.
Okay, so that is going to be our z-axis. So how can we actually represent that alignment or direction for our vector orientation? For example, for most cases, towards right x-axis is considered to be the positive x-axis. On the left side we have negative x-axis, and on the top side we have the positive y-axis. On the lower side we have the negative y-axis. So how are we going to determine the direction for the z-axis? That's basically where comes the dot and the cross. So that's what we're going to learn first. For the case of a vertical axis of the screen, we use two type of signs to represent two directions. Dots, sometimes given as only dot, or sometimes can be also given by a dot and a circle. So this either any of these two can be used. This means out of the page. I'm using the word page because for all of your description, for your written purposes, you're going to write this experience that out of the page. That page might belong to a book, that page might belong to your exercise copy, or might be your actual exam paper. So out of the page is basically the thing, but in a more bigger sense, I can say out of the surface. Or I could also write this just to make sense with you, towards you. I'm writing this bracket word because I'm going to explain using this phrase, towards you. And the other thing that we use is cross, sometimes used only by cross, or sometimes it can be also used by a cross and a circle around it. That means into the page. Or I can write it as away from you. What do I mean by this? These are just basically a way to represent the third axis of a two-dimensional drawing in terms of in which direction are we considering that third thing to work. Is basically required for vector quantities, because magnetic field strength, electric field strength, force, they are all vector quantities. current always travels from high potential to low potential, or you can also say it always flows from positive to negative, or positive to zero, or it flows from more positive to less positive, or from less negative to more negative. You get the point. It always moves from high potential towards low potential. So although current is actually a scalar quantity, but in terms of flowing direction, it does have a relevant nature of flow direction. For example, if I want to give you another example, for example, energy is actually a scalar quantity, right? We all know that energy, joule, is a scalar quantity. But if you consider that, let's say here is the sun. In which direction is the sun giving out energy? It is giving out energy in all three-dimensional direction from the sun. So if you are right over here, are you going to receive the sun's energy in this direction, or in this direction, or are you going to receive it in this direction? The answer is definitely you're going to receive the energy along this direction, not in this direction, which means sun's energy is going to reach to us, if the earth is right over here, in a very specific direction. So although energy itself is not vector, but whenever it relies upon a direction, or whenever, because of the whole scenario, a certain direction get tangled with it, or it gets added to it, it can happen. Which, what I'm going to mean is that current is a scalar quantity. That is perfectly all right, charge over time. But whenever current flows from one place to another place, it has a definitive direction that is always from high potential to low potential. So that direction of current is going to be of useful thing for us. Although current is not a vector quantity, but direction of current is going to be important for us, which we're going to see after a while. So these are the two different scenarios that we talk about for dot of the page. Dot is out of the page and crosses into the page. The easier way to remember this thing is basically the historical background from which these two signs are actually derived from. These two signs are derived from the orientation of an arrow, an actual arrow. Let's say there is a person, figure not drawn to scale, and let's say he is holding up a bow and about to shoot an arrow. So if you consider the structure of an arrow, if I try to draw an arrow, let's say this is a typical arrow, and here are the tail feathers. So the idea is, if a person shoots an arrow, I mean, if the person's eye is right over here and he is shooting the arrow, he's going to see the arrow leaving from this point, from this person. So he's going to see the tail feathers in front of his eyes, which is represented by this shape. So the cross represents the rear view of the tail feather of an arrow. However, if an arrow is shot at a person, for example, there is just a person over here, figure not drawn to scale, and definitely not realized. You are not trying to shoot a person with an arrow, but let's say the person is over here. This arrow is going to be shot towards this person's eye. So if there is a person to which an arrow is actually shot, this person is going to see the tip of the arrow, which is represented by the dot. So basically, the dot represents towards you, or in for a two-dimensional page case, it represents out of the page, and cross means away from you, or for a two-dimensional case of a paper, we refer to it as into the page. So that's the key idea. Now comes the very famous experiment of, whose experiment was it? Clerk Maxwell? No. Michael Faraday? Wait. Where is my book? Please, just a second. I believe it was by Michael Faraday. Just a moment. Yeah, it was done by Faraday's rotation experiment, and the magnetic effect of current was actually first discovered by Ørsted. Ørsted is actually a very famous scientist who came up with this whole idea to begin with. But scientist Faraday eventually went ahead to do significantly detailed experiments on them. So Michael Faraday's name is actually more attached compared to Ørsted. But anyhow, I'm going to explain to you what the electrical behavior, magnetic behavior of a moving charge looks like. So first of all, we need to recall that what we mean by conventional current. Conventional current is the imaginary historical mistake, decaying direction of current, which was considered to be flowing from positive charge towards negative charge out of no physical proof. So we still till date do that, and that's what conventional current is. So conventional current, in other terms, can be considered to be a flow of charge of positive charge particles. So here's what I mean. Let's say we have a setup where we have a positive charge plate over here, and we have a negatively charged plate over here, and they are kept at a very high voltage in between them, like super high voltage. So uh, if it is possible that if we apply enough voltage across these two plates, at some point they're going to start to produce spark in between them. Basically what happens in that for the case of a lightning. So let's whenever the spark happens, what actually happens? A group of electrons split off from the negative plate, and they use all the surface shell of the atmospheric air molecules or the carbon dioxide molecules or different atoms, and they produce a closed path to reach to the positive plate. And they make multiple of these paths depending upon how much voltage are we producing. So they basically overcome the resistance of the whole gaseous medium of air that exists between the two plates, and that's how they flow. So whenever electrons are flowing in this way, we'll definitely can say conventional current I is flowing that way. So that's one idea that I am to understand. Similarly, if there is such a case, let's say if there is a let's say this is a lead container in which we have kept some radioactive specimen, which is a alpha source. I did not yet teach you the radioactivity part yet, but did you kids ever study about it in your school yet? Anyone? Maybe not. Okay, I'll tell you what. Radioactive materials can have three types of ionizing radiations. One of them is the alpha radiation, the other one is the beta radiation, the other one is the gamma radiation. Alpha radiations are the positive charge particles, which are basically helium nucleus. So basically, if we can somehow strip off the two surface electrons or two shell electrons out of a helium atom, what you're going to be left with is exclusively the nucleus of the helium atom, which is called a helium nucleus. And alpha particles are basically those things which are emitted out of some radioactive specimen by means of radioactive decay process, which you're going to see after a while. So let's say this is an alpha source. So the reason we are placing this within a lead box, now you might wonder, this doesn't look like a box. What kind of box is this? This is actually a representation of a long section of a horizontally held box. So the box actually looks like this. Let's say this is the face of the box. If I try to draw it in a bit of a three-dimensional view, this is how the box looks like. So let's say this is the box. Inside the box, on this way there is a small tiny hole. The hole goes all the way down halfway in the chamber, not all the way inside the chamber. So it goes halfway, and we keep the radioactive material exactly at the bottom of this thing. The reason we keep the radioactive material within a lead box like this is so that the ionizing radiation cannot harm the operator people and give rise to some other type of problems related to radioactivity. Anyway, if we have a radioactive specimen over here, this is an alpha source. So I'm going to label this. This is an alpha source. So let's say it is shooting alpha particles in all directions, but all the alpha particles which are shot towards the lead box, they're going to get absorbed to the lead. Only the few alpha particles which are shot through this opening of this tube, they're going to be coming out in a pretty much straight line, but they're going to be slightly spreading out because of the hole size. So whenever we have positively charged particles flowing in this direction, this flow of particles can be considered to be a current flow that is happening in this exact direction. Point that I'm trying to make in this discussion is that even if we do not have a metallic conductor, that's my point. That's the reason I'm bringing about these examples. Even if we do not have a metallic conductor, or maybe even if we do not have an electrolytic conductor, for example, electrolytic solution, sodium chloride mixed with water, even if we don't have that, it is possible that charged particles can move. And whenever charged particles will move, depending upon what kind of charged particle is moving, we can very well specify the direction of conventional current. If negatively charged particles are moving, conventional current will be in the opposite direction of that. If positively charged particles are moving in some way, then conventional current can be considered in the same direction of that charge particles movement. এই কনসেপ্টটা বোঝা যাচ্ছে কিনা? The charge particle movements can be interpreted as current, even though there is no conductor present. Does it make sense?
Yes, sir.
Any of you, if you have question, please let me know. So what scientific Oersted, actually scientific Oersted did a lot of experiment, and he was actually the first person to find out the magnetic effect of this whole thing. I'm going to show you some experiment that actually scientist Oersted found out when he was doing these experiments, and then I'm going to get into the Michael Faraday's experiment. So let me show you.
Oersted's experiment.
Have a look at this one.
In 1820, Hans Christian Oersted performed a simple experiment and discovered the magnetic effect of electric current. The experimental setup, similar to the Oersted's experiment, which led to the discovery of magnetic effect of electric current, is shown in the animation. A conductor or conducting wire AB lying in north-south direction is connected to a battery V through a commutator or tapping key K and rheostat RH. A magnetic compass needle NS is placed just below the conductor AB. Initially, when no current passes through the wire AB, the magnetic compass needle shows no deflection. When an electric current passes through the wire placed above the compass needle, the magnetic compass needle got deflected from its normal position, which is along north-south direction. On reversing the direction of electric current through the wire, he observed that the magnetic compass needle got deflected in the opposite direction. Also, the deflection of the compass needle increased when the magnitude of electric current through the wire was increased or when the compass needle was brought closer to the wire.
Okay, that's just very simple setup. So I'll just try to make sense with you what is actually happening over here.
Hi friends, I'm going to show you some pictures and
So let's have a look. The Oersted experiment. There is no such thing as a red hand rule. I think you are trying to write right hand rule or left hand rule. Yeah, there is a thing called left hand rule, and there is also a useful rule that can be said to be right hand rule. We're gonna get into that. Yeah, there is definitely the left hand rule. We're gonna talk about that right now, just after a while. Have a look. One of the things that I need all of you to remember is that whenever any magnet is placed within a pre-existing magnetic field, it tries to align itself so that the pre-existing magnetic field lines can enter through its south pole and come out of its north pole. So it's basically gonna try to agree, I'm gonna use that word, or it will try to align its own magnetic field lines in line with the pre-existing magnetic field lines so that it can perfectly it can exist within the magnetic field with the least amount of disturbance. That's how the deflection of magnetic behavior works. So what I'm trying to mean is that if we have a needle magnet, then let's say that is this one. So let's say we have a needle magnet of this much. Is there a way that I can rotate this thing, this whole drawing? I actually can. Okay, beautiful. So let's say if we have in a certain location, if let's say this is the north pole side and this is the north pole side and this is the south pole side. So if we have in some location produced a magnetic field that looks like this, and if we bring about this needle magnet onto this surface, let's say over here, this is gonna rotate in this orientation so that the north pole is perfectly aligned with the leaving side or the output side of the field lines, and south pole is gonna accept the field lines. If you bring about into some other field, for example, in some other location, if we produce a magnetic field that works vertically downwards like this, and if we bring about this needle compass over there, this thing is going to rotate itself and align itself in this orientation. Point them time to help you remember is that magnetic field lines will always cause the rotation of a freely rotating, freely movable magnet. This is exactly what scientist Oersted found out when he actually doing this experiment. So what he actually saw that, let's say this is a piece of wire AB, and we are going to send current through this wire with different direction by using a commutator switch. A commutator switch is basically a switch that can reverse the current flow direction. It's basically, as it was shown in the figure, it had this kind of two pieces of half moon metal strips facing each other, and there was a central metallic bar. So I'm gonna, let's say I'm gonna draw the bar right through the middle over here just to avoid confusion. So let's say one end of the wire is connected over here, and the other end of this wire was connected to a rheostat. So I'm just going to show this rheostat as a variable resistor, and then we had a battery. So let's say this is a battery, and that's basically our main circuit. So what's going to happen if we now close the switch? The current is going to, let's say if we now close the switch by, and I say yes, beautiful. If we now rotate the switch by rotating in this manner, what's going to happen? Current is going to travel, have a look, current is going to travel from the positive end of the battery to the rheostat, going to this circle, and then it's going to travel through here, and then it's going to travel through here and go out through here, and this is why how the current is going to flow back to the negative end of the battery. We can do the reverse. How? If I now have a look, I'm just doing Control Z so that I can get rid of the lines. Alternately, what we can do, let's say the rheostat is over here. We do not change any of the connection type. We are simply going to reverse the connection positions of this rheostat switch. And let's say if we rotate it in this manner, then I'm not doing it right. Where am I messing up? Hold up, hold up. In this case also, I forgot how the commutator switch works. It's a bi-way switch, no. It's a both-way switch, no. আরে commutator switch সার্কিট সিম্বল ভুলে গেছি দূর হ। 1 মিনিট প্রমাণ আচ্ছা, আমি কম্পিউটার সুইচের অপারেশন ভুলে গেছি। এটা আমার দেখা লাগবে। কম্পিউটার সুইচ অনেকদিন পড়াই না, so ভুলে গেছি। I'm really sorry about that. So I'm going to rub off the computer switch right now. I'm just going to reverse the current direction by alternating the battery switch over here. So disregard the computer switch. I'm really sorry about this. I feel like stupid, pretty big stupid. Definitely look at it. Achha. Anyway, let's say this is our full circuit and we want to do multiple things. So what the scientist Oersted did, this is what he did, this is what he actually did. He placed a very simple needle compass over here that was hanging from a single point support, let's say over here. And he also had a mechanism to hang this exact needle compass, which has north and south pole, on top of the wire as well. So he could place it actually in any position he wanted. So this is something that he could do. And this support is made up of insulator material, whereas the needle compass is essentially made up of steel because it has to be a strong magnetic material so that it can retain the magnetism. So what he found out, when the, let's say if the circuit is open, let's say if the switch is open, so I'm trying to draw a switch over here, let's say the switch is open, this this needle compass just aligns itself with the geographic north pole and south pole, very much like a magnet. If it is allowed to hang freely, it will align itself with the Earth's magnetic field lines. Then the moment the switch is closed, it was seen that this thing rotates from its original position, or it misaligns with the geographic magnetic field, Earth's magnetic field, and then realigns itself in a certain direction. That's what he saw. And then what he also found out that, let's say after we close the switch, let's say this needle compass, I cannot select exclusively this part, can I cannot. So let's say after closing the switch, the magnet is actually going to realign this way. So at the bottom, the alignment of this magnet is gonna look somewhat like this. Now I know this because I just know, but I'm going to explain this why this works. So he found out whenever it was placed at the below the wire, he found out that this was the orientation. And then when this same needle compass was brought above the wire, the orientation of the magnets needle compass started to look like this. The north pole came up over here and the south pole came up over on this other end. And as he keeps on rotating this in different position, the orientation of this needle compass in different places around the wire, as long as the current was flowing, it was continuously changing for different positions. So he was interested in what was actually happening. There are different ways to explain this whole phenomenon. For your syllabus volume, the way it is explained is in terms of the magnetic field line. So that's what I'm going to go by. Whenever any wire carries current, it produces a magnetic field around itself following the right hand grip rule. The right hand grip rule is like this. Sometimes also called the right hand screw rule. Let me fetch up a picture. This is the right hand grip rule. So this is basically, first of all you have to be very careful to understand / remember which is your left hand and which is your right hand.
স্যার এটা তো ফ্লেমিংস রাইট হ্যান্ড অর লেফট হ্যান্ড রুল না
Nah, it is your right hand grip rule, which looks like this. You grip your 4 fingers and extend out the thumb. That's your right hand grip rule. Fleming's right hand rule by left hand rule, I'll introduce you to those things as well. So right hand grip rule is like this. So you close the rest of your fingers, all the 4 fingers, and the thumb, and extend the thumb, and that gives you a 3-dimensional orientation scenario. How? I'm going to explain that to you. But what I want you to understand that, although I shouldn't be telling you this, but I'm still telling you this because some kids actually might find this difficult. Do not mess up your left hand and right hand. If in any case you forget what is your left and what is your right, especially in the exam hall, this is something that you can do. I came to learn about this mechanism from a teacher, and I still to this date I teach the students like this. Remember the alphabet in a linear pattern: A, B, C, D, E, F, and then J, K, L, M, N, O, P, Q, R. So You see, between the two letters L and R, L is first and R is on the right side. So your left side is the left and your right side is the right. So try to visualize the whole alphabet in a single line, and that pretty much always gives out the left and the right positions perfectly. Just in case if you forget, I'm not assuming that you should or you would, but if you do, this is what can help you. So the right hand grip rule actually works for two different cases. It can work for a single wire. It can also work for a solenoid. Solenoid কি জিনিস সেটা একটু পরে বলতেছি আমি। So this is the right hand grip rule. So the idea of right hand grip rule is that for a single piece of wire, try to understand, I'm gonna write this single wire. For a single wire, the thumb represents current direction. And the rest of the fingers actually they represents a circular direction around the wire. So it's basically like that. If there is a wire or there is a conductor that is carrying the current, and if you wrap your right hand around that wire and align your thumb in the direction of the current flow, then you're gonna come up with this thing, and the rest of these fingers are gonna give you the direction of magnetic field around that wire. Now this is the important part. Direction of magnetic field around that wire. This preposition is very important and not to be messed up with. So the interesting part is that the magnetic field is produced around the wire in concentric cylindrical shape like this. Although here they are showing only a circle, but this is only applicable for one section of the wire. If you consider the total length of the wire, there are many concentric circles one on top of another, which is basically producing hollow cylinders. So one way I can show you this like this, hold up. Yeah, take a look at this picture. So let's say this is a conductor which is carrying current from B to it is carrying current to the left through this wire. So I is labeled to the left. Can everybody see this figure? Can you see
Yes,
it?
sir.
The current is going this way. So if we use the right hand grip rule, so the thumb is aiming in the current direction, and the rest of the fingers, so the curl of the other fingers is representing the magnetic field lines along the entire length of the conductor, which means that magnetic field is existing all over the wire. It's not exclusive for a specific single location. So it is located in all the positions like this. So we have the magnetic field pretty much along the whole wire. The reason I was speaking about hollow cylinders, I mean, if you consider this shape extending all over this wire, so all of these inner circles joined one after another is going to give you one small hollow cylinder. All of those second circles are going to give you another hollow cylinder. So all of those hollow cylindrical shapes are going to be concentric, and their axis is going to be exactly the conducting wire. So that's basically how the magnetic field is produced. And let me just see if we can find out a actual three-dimensional figure over here, if it's possible. Once again, having three-dimensional figure in a two-dimensional piece of paper is actually pretty difficult. I think this is the best figures that we have that we need to work with. This is actually a pretty good one, but this is actually what happens for same direction current or opposite direction current, which I'm gonna get to you just after a while. But okay, that was my point to begin with, that whenever we have a wire carrying current around it, for example, this is also a pretty nice figure. So you can see that we have concentric circles around the wire just like that. So we have, when the current is going upwards, we have circular current direction. You don't have to consider all of those differentiate formula. These are not part of our syllabus. I'm just trying to show you the orientation of the fields so that it makes sense. So what is actually happening for this specific wire is that whenever current is flowing by, if you consider the right hand grip rule, try to understand, use your right hand grip rule and assume that this wire AB, which is now flowing current from A towards B, assume that this current is flowing current to this direction. So aim your thumb to your right, aim your thumb to the B point, and assume that the wire is flowing through your grip. So that can tell you that above the wire, the field lines are gonna be penetrating out of the page. So it means on top of the wire, the magnetic field lines are gonna look like dots, because this is where the magnetic field lines are coming out of the page. They're gonna bend down, and at the bottom of the page, these field lines are going to enter into the page. Does it make sense? I'm only drawing the two positions over here. I could show you another position just to make sense. That is, field lines are actually coming out above the wire, over here. They're traveling over the wire. So if I just draw a bit of a curved view, they're traveling over the wire, and then they are entering into the page over here, and then eventually they're passing through the page and coming out on the rear side over there. So this is the point through which the wires are coming out, and this is the point where through which the magnetic field lines are going in. And you actually have a lot of those things in a single positions, and all of these vertical positions are the coming out position of the magnetic field lines, and all of these lowest positions are the getting into the page for the magnetic field lines. I'm showing you a bit of a tilted view. So these ellipses, which are appearing to be ellipses, are actually circles. But because I'm trying to show you a three-dimensional view of a three-dimensional figure, that's why they are appearing to be an ellipse. But my question is, did you kids understand the idea of this dot and cross about the how the field lines are coming out of the page and how the field lines are getting into the page? এই আইডিয়াটা বুঝা যাচ্ছে কিনা? Try to rotate your right hand figure. Okay, I can actually start going for the camera today. Give me a moment. Camera. Okay. Is it not connected to my USB? It's connected to my USB. Can you see me? Am I visible?
Yes, sir.
Yes, sir.
So you are seeing the screen, and on the side you are seeing my image, right?
Yes, sir.
I mean, the screen is also visible, right?
Yes, sir.
Yes, sir.
Okay, so this is what I'm trying to mean. Try to understand. So let's say this is my brother's prescription. Okay. So let's say this is the actually I can draw. Let's say this is the piece of paper. So let's say the current is flowing. You can see it.
দেখা যায়, দেখা যায়, দেখা যায়।
Let's say the current is flowing this way. Here is A, here is B. So if I hold my finger like this, so what I want you to visualize is that, I mean, let's try this. Hold on, I'll get a piece of paper that I can just draw. Got it. Okay, let's say this is the piece of paper that is carrying this is the AV wire that is carrying the current. So the way the magnetic field lines are going to be produced is that we're going to have one field, let's say one field line. I'm talking about one field line right over here. So let's say one field line is going to come out from this point, make it so try to have a look at the tip of the pencil. So try to have a look at the tip of the pencil. So one film is coming out over here, is going to travel out, take a curve, and then penetrate through the page right at the bottom over here. So it's going to come out through this hole. So it's coming out over here and then bending its way path and eventually entering at this point. This is why we're going to label this coming out point as a dot, and we're going to label this point as a cross. This is equally applicable for, so the top one is labeled as a dot and the bottom one is labeled as a cross. Can you see the cross?
Yes, sir.
I think you can see it now. So
Yes, sir.
what I'm trying to mean is that whenever we're going to hold our hand around the wire in this orientation, let's say in this orientation, so the thumb is represented this way. So if you just try to use your finger motion, what you'll see that if my wire is considered to be within my grip, let's say if this pencil is the wire, so above the wire, the fill lines are coming out of the page. So what I want you to visualize that this wire is, let's say, within the page. So let's say this is the piece of page, and let's say the wire is located right here. Okay. So now if I try to put my right hand finger over here, on top of the wire, the fill lines are going to penetrate out. They're going to fall down in front of the wire. So this is the down direction. And under the wire, they're going to get into the page. Do you understand my point? Rohan?
Yes, sir.
Yes, sir.
এই মানে পার্টটা বুঝা গেছে কিনা যে বেন্ডিংটা কেন হচ্ছে?
Yes, sir. বুঝে গিয়েছে।
That's one thing. The other thing is that, so this is why I can actually write over here a lot of dots on top of the wire and a lot of crosses at the bottom of the wire. This is what gives us the three-dimensional representation of the magnetic field for a single piece of wire. To be honest, drawing only one set is never good enough because the field is actually distributed further away from the whole thing, and it is going around in all directions. So it's actually a gradually increasing field. So, but we do not bother to draw all of those field lines individually for our purpose. We are basically trying to show one set of field lines just for the sake of representation. That's basically what your syllabus covers. We are not getting in the way of that. So point to be understood, there is actually one interesting question over here, is that okay, let me just give you one question. So there are many different figures that actually can show up for the for example, if you have an actual piece of paper, let's say that's labeled like this, and they have shown you a current carrying wire that's vertically coming up like this, and this wire is actually penetrated through the center of the page. So this is sort of a three-dimensional figure. So in this case, the magnetic field lines around the wire are gonna look elliptical shape like this. And what is important whenever, if you ever have to draw these lines, is that the farther you go, the field lines have to be really far apart from each other, because the more you go away from the wire, the magnetic field is going to become weaker. So the way I have tried to draw this figure, have a look, have a very good look. This is the location where the whole of the wire is. Now take a good look. The gap between these two field lines is smaller compared to this gap. This gap is once again smaller compared to this gap. Do you see it? So within my drawing, I have tried to maintain increasing gap behavior, because it is very obvious close to the wire we're going to have a strong magnetic field, farther from the wire we're going to have a weak magnetic field, and obviously really important, never forget to give the duration of the field lines. Actually একটা duration দিলেই হয়, আমি for no good reason multiple duration দিতেছি, একই wire উপর multiple duration, second duration দিতেছি, but if the current is going this way, this is the orientation of the magnetic field orientation for a single piece of wire. এই পর্যন্ত বুঝা গেছে কিনা everyone? Any question? আচ্ছা, এরপর যেটা দেখো সেটা হচ্ছে যে what's going to happen. So আচ্ছা, আমি এই আলাপটা শেষ করি। সেটা হচ্ছে because the magnetic field around this single piece of wire has a shape like this. So if you do place a needle compass right at this location, it is going to align itself with the magnetic field lines like this. It is going to align itself in such a way so that the incoming magnetic field is going to be the south pole side and the leaving magnetic field is the north pole side. If you place it right over here, for example, it's going to behave like that. Right? The north pole is going to be on the right, south pole is going to be on the left. If you place it, let's say, right behind the wire, you're going to have just the opposite behavior. If you place it right over here, for example, you're going to have it perfectly aligned with this thing, where the north pole is going to be on this side and the south pole is going to be on this side. Sometimes the examiners can also ask you what's going to be the orientation of the needle compass. Just draw a needle compass and label north pole and south pole. If the plotting compass is placed somewhere in between the magnetic, for example, somewhere over here, they're going to ask you that if the plotting compass is placed in this position, what will be the orientation of the magnetic field lines? So you have to use your idea very carefully. Try to understand. This is a three-dimensional picture drawn on a two-dimensional plane. It means we are trying to represent circles represented as ellipse. If I draw this same figure when looked from vertically above, for example, if I'm trying to represent this whole figure in an actual two-dimensional scenario, how is this figure is going to look like? Let's say this is a good rectangle. This is the whole page. Let me use green once again. Okay, that might be actually good for us to keep up. So let's say please become a square. Beautiful. This is the piece of the paper. Look from above. Here is the wire that is coming out. Now I'm only representing this by a dot because in this case, if our eyes are over here, if you're looking from the top, and this is the view of the top view, so then the current is actually penetrating out of the page. So that's why I'm representing this current as a dot, not by cross. This is gonna give me concentric anti-clockwise circle where the gap between the circles should increase. Okay, I'm only drawing 3 over here because drawing the 4th one might be difficult. Now, try to understand. If the question asks you to draw the orientation of needle compass right over here, which basically means somewhere over here, what you need to understand, if the magnetic field lines are all going down in this direction, which means along this entire line, through this entire line, over here, I mean, on the left side of the wire, all the magnetic field line orientations are going to be vertically downwards, no matter where you go. On the right side, all of these magnetic field lines are going to be vertically upwards, no matter how far you go. I mean, as you slowly get farther away from the wire, you're going to have weaker and weaker field. But the direction, that's going to be basically the tangent of a circle along its diameter. At the diameter intersection point, not along its diameter, I mean, at the diameter intersection point. So you're going to have upward magnetic field lines for the whole right side. You're going to have downward magnetic field lines for the whole left side. Eta thik kina polaban eta buঝছো?
Yes, sir.
In the same way, if you consider this for two vertical lines, for example, if I try to draw two vertical lines, let's say the vertical axis over here, on this vertical line, no matter where you go, magnetic field orientation will be always from right to left because they are all making circles using the right hand grip tool. So if you think about your thumb is over here aiming at you, your rest of the fingers are simply going to make the curve in this orientation, in the anti-clockwise direction like that. That's the idea of the right hand grip tool. So above the wire, all the orientation in all the locations, the magnetic field orientation is going to be right to left. Below the wire is going to be always like this. And I could extrapolate this behavior along any other line. Let's say if I draw any other line over here, over here, over here, doesn't matter. You do understand what I'm trying to get at. My point being, if we actually place a needle compass right over here, it is going to align itself with the existing magnetic field orientation. So it's going to be somewhat like this. So where this end is going to be on north pole side, this end is going to be south pole side. Now, how do you draw this over here? Now, this is the point that I want you to understand and have a good look. Is it going to be correct if I draw the needle compass over here like just like that? If is drawing in this manner going to be correct? Over here. Are you getting my question? I'll say the question again. The question has given you this figure, this wire. The magnetic field orientations are also given, and then they have given you a single dot over here, printed dot, and they asked you that a needle compass is placed carefully on this position. Draw the alignment of the needle compass with this pole label. how do you draw that needle compass? That's my question. So this is the top view. So if we draw this needle compass in this manner, is it gonna be okay? Are we gonna score mark for that? What do you think? Yes or no?
Yes.
Okay, that's one response. We have 5 more people. I think most of them have fallen asleep. It's pretty late. Plus, আজকে থেকে স্কুলে ক্লাস শুরু হচ্ছে। তোমাদের কি আজকে ক্লাস ছিল স্কুলে?
অনলাইন ছিল, ফিজিক্যাল না।
ফিজিক্যাল ক্লাস হয়েছে আজকে?
আচ্ছা, আজকে
কালকে থেকে শুরু হবে?
মাস্টারমাইন্ড ক্লাস 10 এর শুরু হবে না এখন।
আচ্ছা, মানে ক্লাস 9 পর্যন্ত হবে?
ইয়েস।
আচ্ছা, মানে ক্লাস 10 থেকে উপরে যারা
মাস্টারমাইন্ডের ধানমন্ডি ব্রাঞ্চ হচ্ছে 6, 7, 8 হবে।
আচ্ছা, মানে সমস্ত ক্যান্ডিডেটদেরকে বাদ দিচ্ছে 6, 7, 8 মানে হচ্ছে মানে প্লে গ্রুপ থেকে 6, 7, 8 পর্যন্ত। আচ্ছা, মানে মেইন ব্যাচে তো 6, 7, 8 পর্যন্ত, মানে হচ্ছে বেসিক্যালি পিচিদের থেকে শুরু করে 8 পর্যন্ত ক্লাস হবে, তাই তো? ফিজিক্যাল ক্লাস
না
হবে
স্যার, খালি 6, 7, 8
নিচেগুলো হবে না?
আমাদের না, পিচিগুলো হবে না। আর হচ্ছে আমাদেরটা এখনো ডিসাইড করে নাই, কিন্তু আমাদেরকে জানাবে আমাদের ফিজিক্যাল ক্লাস কবে নিবে।
I think they want to give a test time to the kids of 6, 7, 8 because I don't know, because for whatever reason they can start, and if things seem manageable, doable, you might be invited. আচ্ছা, ব্যাপার না, যেটা বলতেছিলাম, drawing this needle compass over here in this orientation is not going to be a good idea. I'll tell you why. What you need to understand, whenever we're going to place the needle compass on the piece of paper, we're going to place the needle compass on the piece of paper. And in this case, these edges that you can see over here, which are apparently looking like a parallelogram, they represent the 4 edges of a square piece of paper. Try to understand. This is a 3-dimensional view on a 2-dimensional surface. On a piece of paper, we are trying to represent 3-dimensional view. That's why a rectangular, a perfectly square piece of paper is appearing to be a parallelogram over here. So here's the deal. If we place this thing over here, have a look. This object, I mean, this is the top view, and this is a perfectly good figure. What I need you to understand, along this line, the magnetic field orientation is vertically downwards, which is going to make sure that the needle compass is also going to be vertically downwards for this view, which means the axis line. Let me just try to represent this. The axis line of the needle compass, let's say this is the axis line that goes to the 2 sharp corners of the needle compass. This axis line of the needle compass should be perfectly parallel with this edge. ठीक ना? Isn't that what vertical means in this case? Now, if you wonder, why am I bringing about the edge over here? Because this edge is basically what's going to help you to draw this figure properly. So try to understand. Let me just erase this thing. Drawing this figure like in this manner is not going to be a good idea. How should we draw this figure? We should preferably draw this figure in this way. Have a look. If this is the location where we are trying to draw the needle compass, that needle compass better have its 2 ends so that they are parallel to the edge of this thing. So here you can see over here, I'm trying to give 2 dots. They should be equidistant preferably, but I couldn't draw them equidistant. But I'm trying to find out the 2 dots over here, and now I'm simply going to make up the position of the needle compass like that. Trying my best to make sure that the alignment of the axis of the needle compass, which is right over here, should be, to my best capability, parallel to the edge of the paper, representing that I'm actually trying to draw this thing through the equator region of the page. এই জিনিসটা বুঝছো কিনা বলাবান? ড্রয়িং এ অ্যালাইনমেন্টের পার্টটা বুঝা গেছে যে কেন ভার্টিক্যাল আঁকলে হবে না? কারণ এই ফিগারটা হচ্ছে একটা বোচা ফিগার বা বচকানো ফিগার। We are trying to represent a 3-dimensional scenario on a 2-dimensional piece of paper. So this is definitely not geometrically accurate, but we have to make do with what we have. That's where the parallel alignment comes in for help. So, and you definitely have to label this thing. In this case, this is going to be our north pole side, this is going to be our south pole side, and that basically scores you the mark. Same thing goes if they ask you for any other position, for example, on top of this. For example, if you're trying to draw the orientation of the needle compass, if it is placed over here, this is gonna have its axis perfectly parallel with the top border or the bottom border. So it's gonna be perfectly horizontal because these two sides are drawn to be perfectly horizontal. So no problem there. We can simply draw. Let me draw with black maybe. So you can simply give two dots with so that they make a horizontal line across the designated point, and then you can simply make a needle compass just like that, and simply label north over here, south over here, and you're good. So the alignment of the compass needs to be carefully drawn. Achha. The next thing that is going to happen is that, so what is very important, that if we place the needle compass around in different places, we're going to have different orientations depending on the current flow. And one thing is obviously true, if we reverse the current flow, then what's going to happen? For example, let's just try to find out one of those figures. Okay, got it. This is gonna be helpful. So what we have discussed up till now was a scenario for this case where the current was going upwards and the magnetic field lines were like this. If we just reverse this, so if the current flow happens this way, downwards, then simply the magnetic field line orientations are going to be changed, because in that scenario, let's say if I just try to draw another scenario, let's say this is a piece of paper where this is the hole through which the wire is going through the paper. So this is the physical wire, but in this case, if the current is going this way, then you have to aim your finger aiming downwards, assuming that the wire is in your rest of the fingers. So in that case, the magnetic field lines are gonna be producing clockwise orientation, somewhat like this, and they should definitely be elliptical, not my poor drawing. So hand-drawn figures should be it's difficult to draw good hand-drawn figures. Okay, this is definitely not perfectly good, all right, but figure is not drawn to scale. But you get my point. The directions of the magnetic field lines are simply going to reverse, because the current produced by current carrying wire is always done by right hand grip tool, where the thumb represents the current direction, rest of the fingers represent the magnetic field line orientation. We're going to extrapolate this idea of a single wire into a circular wire, and that's where things become interesting. Let me just show you one figure, and so that it will make better sense to you. Beautiful. Should I take this one or this one? I think all of them are pretty nice. This is good. আচ্ছা, আমি যেটা আমার মতো করে আঁকি, আমি এক্স্যাক্টলি যেরকম খুঁজছি শুভ ওরকম ফিগার পাচ্ছি না। Let me just bring about this idea. Let's say we have a piece of so let's say we are getting back to this wire. Now if I want to bend this wire into a circular pattern, so let me just show you what I mean. Let's say this is a piece of wire, thicker dot. This is a piece of wire, and it's producing a loop of some sort. Now I'm intentionally drawing this loop to be of this shape to give you a bit of an idea of 3 dimension. So let's say This is the battery, and then has a switch maybe, and close the circuit is closed. Okay, we might as well also want to draw some. We might as well connect some variable resistor, so that would be a good idea. So still not a good connection point. Anyway, so this is the part that I wanted to understand. Have a look over here. Let's say now we have made the whole wire into a circle. So what I want you to understand that this is a circle that is shown in a three-dimensional space. Let's say this is our point A, and this is our point A, this corner is our point A, and this corner is our point B, and the current is flowing through the circuit in this way, going up, then flowing this orientation, and eventually going all the way down over here. So now what I need to understand that this wire for each of its individual positions are going to produce a right-hand grip rule scenario. So let's say at this location, the magnetic lines are gonna be like this. At this location is gonna be like this. Are you getting my point, Polaban? এই ফিগারগুলি বোঝা যাচ্ছে না, বোঝা না যাওয়ার কারণ আছে, আমি বুঝাই দিচ্ছি, দাঁড়াও। I just need a sharp eraser. Why can I not? Okay, maybe I can. Try to visualize the dotted parts of the magnetic field lines behind the wire and the solid parts of the magnetic field lines in front of the wire. See if that makes sense. See if that helps for your visualization. Does it help? সামনের পার্টটা হচ্ছে এই সলিড লাইনটা হচ্ছে ওয়্যারের সামনে, আর ডট লাইনটা হচ্ছে ওয়্যারের পিছনে। বুঝতেছো কি বলছে? So the conventional current is passing through this loop in this direction, and magnetic field lines are produced all around this wire in this orientation. And I could fill up this whole thing, but I really don't want to because that's gonna make the figure more messy. But see if you can make sense with these many field line or drawing. Is it making sense somehow? Try to use right-hand grip rule. Try to visualize your thumb onto this wire, and your rest of the finger are wrapping around the wire, giving you left to right magnetic field lines in front of the wire, and right to left magnetic field lines behind the wire. So these dotted lines that I have drawn over here, they are the field lines behind the wire. I mean, if you are seeing in terms of distance from you, first, I mean, if I'm trying to describe this figure in terms of distance from you, first your face, and then as you are slowly getting to the close to the coil, this field lines comes first, then comes the wire. Behind the wire is this field line. So that's the sequence. এটা কি বুঝছো? এই ফিগারটাকে আরো ইজিলি বোঝার জন্য আমরা আরেকটা কাজ করতে পারি। সেই কাজটা হচ্ছে, let's say we're going to cut the wire, we're going to cut this wire in a vertical section, like this. আচ্ছা না, এটা আঁকলে আরো ঝামেলা হইতেছে, দরকার নেই। আচ্ছা, let's say if I want to draw this is actually a three-dimensional, or what we call an isometric view. If I want to draw just the side view, I mean, if you just look at this wire in this way, on the very much on the side, you are not going to see the whole loop. Basically, you're going to see the side view of the circle. So you're going to see this whole circle. এটা দেখা যাবে কিনা সেটা বল। মানে I'm only what I'm drawing over here is basically the wire viewed for this part, because now we are looking from the side. So let's say the eye is right over here looking in this way, so we are seeing this wire. For this wire, the current is basically going upwards. It's not definitely going upwards everywhere. I mean, at this point, the current is coming out of the page, so I can actually label this as a dot. At this exit point, the current is going upwards, and exactly at this point, the current is going into the page, because here the current is getting away from us. So at this point, the current is going away from us. So if I'm trying to draw this figure for only, let's say, I'm going to name this point over here or over as C. So if I'm only trying to draw this figure for the AC part of the wire, this is the view. What I really want you to understand that this is going to produce magnetic field lines where crosses are on the right. Sorry, dots are on the right and crosses should be on the left, following the magnetic right hand grip rule. There should be equal numbers on both sides, but I didn't count on the right side, so I didn't bother to draw equal numbers on the left side, but there should be equal number of dots and crosses on both sides. I'm not sure if there are. If they are not, you have to draw them out with equal numbers. So this is the basic idea of the field line orientation. Now, if we consider this whole thing for the entire wire, there will be a lot of different wires passing through. Now, that figure is gonna look somewhat like this. Let me choose a good figure. Yeah, this one makes sense. I can actually work with this one. Okay, the reason I'm bringing about this figure is to give you a bit of an idea about what I am trying to show you. So let's say this is the wire. Current. No, I just have to put it the other. আচ্ছা আমি এভাবে বুঝাই সমস্যা নাই so I actually tried to explain this for a vertical coil, but here they have used a horizontal coil. This is I'm picking this figure because this is a nice one. So have a look. The current is coming in over here in this case for through this pathway. So for this part of the wire is carrying the current in this orientation, and the rear part of the wire is carrying current in the other direction. So if we use our right hand grip in every place, we're gonna see that all the inside part of the coil, are having a magnetic field line in the upward direction. Whereas outside the coil, the magnetic field lines are going out, which means if I try to draw all the magnetic field lines, the magnetic field lines inside the coil, they are really congested, or they are really squashed together with each other within a very small space of this much. Whereas outside the coil, the magnetic field lines can actually spread around a lot. For example, these magnetic field lines can be drawn to have a very wide amount of spreading. Do you get my point? But all of these magnetic field lines, which I'm trying to represent over here, they had to squash themselves through this tiny space over here. The reason this is important is whenever the magnetic behavior of this coil will be determined as a single magnetic pole, these inside magnetic field lines, which are concentrated together, they are going to determine the behavior of this coil, not the outside coils, because the outside coils are weak, they are far apart, and the inside field lines are strong because the inside field is strong because the field lines are really close to each other. So although the field lines are coming out of this phase and they're getting into this phase, this is happening, but is the inside field lines, I mean coiler ভিতর দিয়ে যে field line গুলো ট্রাভেল করতেছে, ওই field line গুলোর বিহেভিয়ার থেকে আমরা এই coiler actual magnetic properties গুলো পাবো. And interesting for you to see, have a look. If you consider this coil, let me just draw this coil over here. Let's say this is the coil that we have, current coming in, a bit of a elliptical shape, and current coming out. Beautiful. What you should see that এই ফেজ থেকে আমাদের ম্যাগনেটিক ফিল্ড লাইনস গুলো বের হচ্ছে, ঠিক না? আর এই ফেজে আমাদের ম্যাগনেটিক ফিল্ড লাইন গুলো ঢুকতেছিল। আমি ইচ্ছা করে এই ম্যাগনেটিক ফিল্ড লাইন গুলোকে ডিসকন্টিনিউয়াস রাখলাম তোমাদেরকে কনভিন্স করার জন্য। এখন একটা জিনিস চিন্তা করো, বার ম্যাগনেটের প্রপার্টি কি ছিল? যেই পোল থেকে ম্যাগনেটিক ফিল্ড লাইন্স বের হয় সেটাকে আমরা বলতাম নর্থ পোল, আর যেই পোলে ম্যাগনেটিক ফিল্ড লাইন্স ঢুকে সেই পোলটাকে আমরা কি বলতাম? সাউথ পোল বলতাম না? তার মানে if we have a comparison with this figure with this one, we can say that this top face of this coil can be considered to be a north pole face, whereas the bottom face can be considered to be a south pole face. The phase through which the field lines are getting in can be considered to be the south pole phase, and the other phase through which the field lines are coming out, that can be considered to be a north pole phase. Does this idea make sense? That a single wire, when it is bent in a loop, it gives us two opposite face of a magnet as a slicer. So this is basically working like a magnet, like a ruti, basically like a ruti. রুটির একটা ফেস হচ্ছে নর্থ পোল ফেস, আরেকটা ফেস হচ্ছে সাউথ পোল ফেস, বাট দ্য বর্ডারটা হচ্ছে অনেক চিকন। এই পার্টটা কি বুঝতেছো বলবান? ঠিক আছে। এখন এই একটা সিঙ্গেল কয়েল অ্যাকচুয়ালি অনেক বেশি ইউজফুল না, বিকজ ইট ডাজন্ট প্রডিউস সো মাচ অফ এ স্ট্রং ম্যাগনেটিক ফিল্ড, বাট ম্যাজিক হ্যাপেন্স whenever we don't have only one of these coils, rather we stack many of them one top of each other. So আমরা যখন এরকম একটা কয়েল ওরিয়েন্টেশনে যাই and we start to send current through this one, then we are going to have one north pole south pole. So let's say north pole south pole stacked upon another north pole south pole, and the north pole south pole, and the north pole south pole, and then also there'll be so many of those individual coil magnets stacked one on top of each other. So basically what you're going to have, you're going to have one coil with north south placed upon another coil of north south upon another coil of north south. They should all be of equal height. I am sorry for my drawing quality. So this is the situation that you're going to get. Each of the coil is going to work like a one small slice of a magnet, one face being north, the other one being south, and they're all going to be stacked one on top of each other. So together they are definitely going to produce a far more stronger magnet. And it's essentially true that the strength of this magnet is basically going to come depending upon how many coils are we going to place. If we have a bigger number of this stack, we're going to produce a stronger coil. Or if all of this individual coil produces a stronger magnet. Now if you wonder, how do they produce stronger magnet? By means of how many magnetic field lines do they produce, and how many magnetic field lines will they produce is directly dependent upon how much current do they carry. If the coil carries bigger current, you're going to have more field lines. If the wire carries less current, you're going to have weaker field lines. So if the current is stronger, then we're going to have a stronger solenoid. If the number of turns is bigger, then we're going to also have a stronger solenoid. A stronger solenoid in this case means that a stronger magnetic field producing solenoid. There is a third property that introducing a soft iron core at the center. ওটা কিভাবে কাজ করে সেটা আমি একটু পরে বলতেছি, বাট এই পর্যন্ত বুঝা গেছে কিনা? That how does the single wire can turn into a circular coil, and stacking multiple circular coils can give rise to the solenoid, which basically works like a very strong magnet. And eventually whenever this magnet is going to work, what's going to happen, all the field lines are going to enter to the south pole, they're going to all travel through the north pole, and eventually they're going to all come out on the other side, which means that if this is the coil that we have, magnetic field lines, let me just zoom it out a little bit, magnetic field lines are all going to come out through the bottom, and they're going to all come, so they're going to all come in through the bottom, and they're all going to come out through the top, and all the magnetic field lines are going to be flowing continuously through this, to the core of this solenoid. So this is how the solenoid is going to work. This is very much similar to the shape of a bar magnet. So if you consider a bar magnet, north pole and south pole, magnetic field lines coming out of the north pole, magnetic field lines getting into the north south pole. So we can actually produce an electromagnet that is produced by current without the presence of any magnetic material whatsoever. I mean, this wire can be made up of aluminum, this wire can be made up of copper, this wire can be made up of iron also, this wire can be made up of an electrolytic solution for all I care. But as long as this wire is, this path is capable of carrying current, this thing can work like a magnet. We don't essentially need any magnetic material to create this magnet. That's the beauty of it. And interesting enough, we can make this magnet appear and disappear at our wish. As long as we're going to flow current through it, this coil is going to work like a magnet. The moment we're going to switch off this current, this magnet is going to be vanished. So this is sort of like a magnet that can work as we want, and that gives us a very large amount of flexibility, especially for industrial purposes. যেটা নিয়ে আমি ইনশাআল্লাহ নেক্সট ক্লাসে আরো ডিটেইলস আলাপ করব। এনি কোশ্চেন সো ফার? সলিনয়েডের আইডিয়াটুকু প্রাইমারিলি বুঝা গেছে কিনা? আমি নেক্সট ক্লাসে সলিনয়েড নিয়ে আরো অনেক কিছু বলবো, বাট এই পর্যন্ত বুঝা গেছে কিনা? বলবান?
Yes, sir.
আচ্ছা ঠিক আছে, থ্যাংক ইউ ভেরি মাচ, আসসালামু আলাইকুম।
স্যার
তুমি
স্যার বই কবে পাবো?
তোমরা কালকে থেকে বই কালেক্ট করতে পারো, বই সব প্রিন্ট হয়ে গেছে। আর আজকে আমাদের শুরু ক্লাস শুরু করব।
আর আপনি কি ফিজিক্যাল ক্লাস নেওয়া শুরু করবেন?
যদি স্কুল খুলে যায় তাহলে ইয়েস, যদি স্কুল না খুলে তাহলে নো। I am not going to start voluntarily on my own because that's going to be a difficult thing to achieve for most of kids or for all the kids. But যদি স্কুলে যদি physical class না শুরু করে, then I'm going to show up in Dhaka and eventually start physical class. And if physical classes do get start, I intend to do labs as well, provided we have enough time available. I mean, পুরো কোর্স না হলে হয়তো আমি তোমাদেরকে মক নেওয়া বা হচ্ছে হেডস আপ দেওয়া বা কিছু প্রিপারেশন ক্লাস নেওয়া, if you kids are interested we might also go get into that, provided physical class.
স্যার আমাদের মাস্টারমাইন্ড
বলো বলো।
পেপার 4 কবে থেকে শুরু করবেন?
পেপার 4 শুরু করব, এটা কি মাস? সেপ্টেম্বর তো? অক্টোবর থেকে। হ্যাঁ
স্যার আমরা রিডিকিউটি কোন শুরু করব?
রেডিটিভিটি জি ম্যাগনেটিজমে পড়ে। রেডিটিভিটি অ্যাকচুয়ালি কন্টেন্ট খুব ছোট, ওটা বেশি মানে ওটাতে অল্প কিছু ম্যাথ আছে এন্ড দ্যাটস ইট। সো রেডিটিভিটি কন্টেন্ট খুব ছোট, মানে তোমাদের টোটাল যে 6টা সেগমেন্ট আছে সিলেবাসে, এর মধ্যে রেডিটিভিটি হচ্ছে একটা চ্যাপ্টার একটা সেগমেন্ট, সো এটা প্র্যাকটিক্যালি অনেক পিচ্চি। এটা কার ছবি? এই যে বড় আয়রন ম্যানের ছবি দেওয়া।
স্যার আমার আছে।
আচ্ছা আছে, এই ছবিটা অনেক সুন্দর। এই স্যুটটার যেন কি একটা নাম আছে?
আলবাস্টার
না না না,
অর ভেরোনিকা।
ভেরোনিকা, এক্স্যাক্টলি I was looking for that name. জারিন কিছু একটা বলতেছিল।
না স্যার আমি
I had a question.
আচ্ছা কে এটা? হ্যাঁ সামিরা বলো।
আপনি কি পেপার 4 করাবেন না পেপার 3?
I can go for both. এখন সিচুয়েশন হচ্ছে যে তোমাদের স্কুলে তোমাদেরকে কোনটা নিতে বলে, or in other terms if I for the lack of a, I really want to pause the recording before